All right, let's take a look at the second half of the Green's theorem lecture, which looks at two-dimensional flux, or flux across a curve or line segment. Now, some of this information about flux is covered in section 16.7 within the textbook, but most of the topics we'll be looking at, pretty much anything to do with two-dimensional flux, is not covered in our textbook. So if you'd like more information on flux in general, feel free to do some of your own research. If you've taken a physics class before, the flux that we're going to be talking about here is the same type of flux that we would use when calculating, say, electromagnetic waves and stuff like that. So electromagnetic flux and this flux are much the same topic. This is just the mathematical tool used to calculate electromagnetic flux. But let's get started. So first, say we've got some curve R of t. In this case, it's a circle. And I can find a tangent line, which is the item drawn here in magenta. And if this thing is parameterized like the unit circle, where it starts on the positive x-axis and moves counterclockwise, then the natural tangent vector we'd run into is the one that points toward the lower left. So that purple tangent vector that I have drawn in. Keep in mind that if the tangent vector went up the other direction, so to the upper right, that would also be a tangent vector, but we would probably get the items negative partial x, negative partial y, if it were going in that upward direction. But if we're looking at that lower left, again, because of the way that this thing is parameterized, the standard x partial, y partial tangent vector is going to point toward the lower left. So that's a tangent vector, but the thing that we really want to talk about this section are normal vectors. So here I've drawn in the two possible normal vectors that we could have within this 2D space. The first one in blue and the second one in gray. Both of those are normal because they are perpendicular to the tangent line. It's just that one points out of the circle and one points into the circle. And we'll end up coming back to this idea of pointing out or pointing in as an orientation for a normal vector. Here we're talking about out versus in, but in a moment we're also going to look at up versus down as two orientations for our vectors. One thing I want to notice about the way that these are labeled, I've got that the blue normal vector is the vector partial y is in the x component, and the negative x derivative is in the y component. And looking at the gray one, I've got the negative y derivative is in the x component, and the x derivative is in the y component. So when we're looking at getting a normal vector, the x and y derivatives switch places. The reason for that is that if I wanted to find the slopes of any of these, both the tangent vector and the two normal vectors, I would want the y position over the x position. So the slope of the tangent vector and the slope of that tangent line is the y derivative divided by the x derivative. And if I calculate the slope of that blue normal vector, I get negative x derivative over y derivative, which is the same as negative 1 over the slope of the tangent vector, which is the property that we get with perpendicular slopes, right? Perpendicular slopes are always opposite reciprocals of one another. And we can look at the calculation for the slope of the gray line and see that it comes out much the same. We still end up getting negative 1 over purple m. So 1 over the slope of the tangent vector. So it doesn't actually matter for comparing a perpendicular slope, whether that negative gets attached to the numerator or the denominator, but it will matter when we're determining orientation. But the exercise here is to just show that both of those normal vectors have a slope that is perpendicular to the tangent line. So yep, the slopes of normal vectors and tangent vectors are perpendicular to each other. And these normal vectors are going to become quite important. All right, so after a brief review of those normal vectors, now let's start talking about what Flux actually is. Listed here, I've got some two-dimensional vector field that's passing through a curve C. So C is this this maybe blue curve that's going across the page, and the vector field is represented by all the orange and red arrows. So that curve C can have a normal vector associated with it. It will change over time, but I've got one instance of it drawn in. And if I want to talk about what flux actually is, it is a measure of how much a field flows through some curve. When we look at 3D flux, we'll be looking at some curve flowing through a surface. I usually think of it like a net that flux can capture a certain amount of a field based on its orientation to that field. But if we're sticking with a two-dimensional view on flux, which is what we want for this section, I want to be looking at how much a field flows through a curve. So perhaps imagine this curve as a dam on a river. So our vector field represents the flow of the water in that river. And we've got this dam represented by the curve C. And the flow at any point would be a measure of how much of the flow of that water is passing through the dam versus deflecting off parallel to the dam. So if we look at the flow at a single point, if I want to get the amount of that field that's going directly through the curve, I want the projection of that vector F onto the normal vector N. So again, I'm projecting this field onto the normal vector. I'm projecting that F, that red vector, onto the blue normal vector. And if we recall some information from all the way back in section 12.3, we know that the component of a vector in a certain direction, so in this case, the component of F in the direction of N, is equal to F dotted with the unit vector for the direction N. So N over magnitude N will give me the unit vector in the N direction, preserving only the component of F that points in the N direction. So if I look at the flow through a single point on this curve, it's going to be F dot N, which I will bring that up in just a moment. So the flow through a single point is going to be F dot N. The flux then is the flow through the entire curve. So rather than just the flow at a single point, I want the flow through all points that are on this curve, which means I want to integrate that flow across the entire curve. Which means we're going to need a line integral in order to do that. So if I use capital N to be the unit normal vector, the thing that I want to integrate is F dot N, because that will give me the component of my field that flows in the direction of N. And then I want to integrate that along the entire curve. So I look at the flow that goes through every point along that curve. Meaning we can break this particular, so then the flux is the line integral of F dot N times ds, which we're going to get to in just a moment. But we can start breaking that apart into some more usable pieces, particularly if we have a parameterization for our curve, that being r of t, then this integral becomes f of r times, written back in, n over magnitude n, so we can just use a normal vector that we might get from r, multiplied by the magnitude of the derivative of r dt. If we recall back to line integrals, which is in section 16.2, we know that ds is going to be equal to the magnitude of r prime times dt. as long as we have a curve that can be parameterized by r. So again, ds, we need to change that back to dt, so that instead of looking at trying to move through some awkward curve in space, we can just move along the line that's going to be on the t-axis. We can convert ds into dt, just with that magnitude of r prime getting multiplied in. So that is flux, or at least how to calculate flux in a two-dimensional space. Let's go back up to the picture for just a moment and tie together the two things we've already talked about. So flux and flow and all that, plus the idea of normal vectors and how they can have different orientations. So for this particular curve, let's pretend it's a dam again, going back to the example from earlier. I want to think of the dam as having two separate sides. There is a downriver side and an upriver side, or an outward side and an inward side. Doesn't particularly matter what we call them. The part that is important is just knowing that there are two separate sides to this dam. Because right now, the normal vector that we're looking at is looking at the flow of water that goes forward through the dam, that goes downriver through the dam. But we could also have a normal vector that points in the exact opposite direction and is still n. But now if we use this other normal vector, the one that goes backwards, we'd be looking at the flux of this river that goes upriver or backward through the dam. So our choice for the normal vector just determines which item we're looking at. Are we looking at the flow of the river out of the dam, or are we looking at the flow of the river back into the dam? So that's where our orientation is going to be important. But enough of all that high concept stuff. Let's try and apply this to an example. So we're going to consider the field x plus y and x squared plus y squared as our two components. And I want to find the downward flux across the line segment from 0, 0 to negative 6, 0. So when we say that we want the downward flux, this part right here, that means in a two-dimensional sense, the y variable is our up and down variable. So if I want the downward flux through a line segment, I want the normal vector that points in the negative y direction. If I had instead said I wanted the upward flux, I would want the normal vector that has a positive value in the y component. So the way that we can go about getting a normal vector is we can just we already saw it's the y derivative comma negative dx derivative. So I'll plug those pieces in, figure out what my normal vector should be. And then once I have a normal vector, I'll either take that vector as is, or I'll multiply the whole thing by -1 so that I can get my y value to look correct. Again, in this case, I want my y component to be a negative value because I want this thing to be downward. But if I instead wanted it to be upward, I would take the normal vector that has a positive value for its y component. All right, so I've taken the liberty of parameterizing this thing for us already. For just going from 0, 0 to negative 6, 0, our parameterization should be negative 6t comma 0, t going from 0 to 1. If I plug in those values for x and y, I get the value of f shown in that second box. But the interesting part is going to be finding this normal vector. So if we do that, our normal vector should be plus or minus the y value of the derivative, which is 0. And then going into negative, the x value of the derivative of r. so that I'm getting the x value from this -6 in R prime, or rather, yeah, I'm getting the y value from that -6 that's in R prime, and I'm getting the x value from this 0 that's in R prime. Because again, the x derivative and the y derivative switch positions if I'm getting a normal vector. Meaning I have the vector plus or minus 0, 6. So to get the normal vector that we actually want, which is the unit normal vector, I'm going to end up wanting to take 0, -6 from our options, because again, we want the downward flux. So I want my y component to be negative, which means of the plus or minus options, I'm choosing the minus option. And it needs to be the unit normal vector. So I'm going to divide this thing by the magnitude of that vector. 0 squared plus -6 squared. Which should shake out to 0, -1. So we can put that in for our unit normal vector n, 0, -1. And now this is mirroring one of the WebWork questions. And it's important that n be listed as the unit normal vector, and then ds get listed out the way that it was defined back in 16.2. Even though we could kind of move some of those pieces around, as we'll see in the next example, for WebWork specifically, it's got to be entered in just so in this sense. So up next, we want ds, or well, we already know ds is going to be the magnitude of r prime times dt, which means we just need to get the magnitude of r prime, which should be the square root of -6 squared plus 0 squared. So that's going to simplify itself out to 6. Square root of 36 is 6. I'm going to fill that in over here. So again, I must have the unit normal vector, and then the magnitude of r prime is the coefficient on dt. If I sub it in for ds. So to then actually solve that line integral, I'll slide over here to the right. I've got that work all done out. I just wanted f of r, which if I start labeling some of these pieces, this piece, f of r of t, times the unit normal vector, which is n, and then multiply that by ds. Put in each of those different pieces, but solving them out so that they can all be in terms of t. But once we have all that together, we can simply take a dot product, multiply the whole thing by 6. This dot product isn't so bad. The x component's just 0. So I've got -36t squared times 6. And 36 times 6, I believe, is 216. And then integrate that thing, plug in 0 and 1. I got -72. So -72 will pop in right there. And I'll have an arrow saying, hey, look over here. All right, let's try that whole mess. Or wait, before we try that whole mess again, let me just talk for a moment about that unit normal vector one last time. I said that I wanted the downward flux, which meant that I wanted the vector 0, -1. If I instead wanted the upward flux, my unit normal vector would be 0, +1. So if the question asked for upward flux instead of downward flux, we just swap out the normal vector and do everything else completely the same. And also, if we just kind of think about what it is that we've actually done here, our line segment goes from the origin to -6, 0, which means move to the left -6. So our line segment is just a horizontal line that's a little bit to the left of the origin. So our normal vector should either point straight up or straight down. Right? If we have a horizontal line segment, then the normal or the perpendicular line to that is going to be a vertical line. Right? Vertical lines are perpendicular to horizontal lines. Tie some concepts together, hopefully. All right, let's try that same problem again. But this time we're going to have a different line segment. So this time we're going to go from 7, 0 out to 0, -7. So we're going to start at a point that's on the positive y-axis, move down left to a point that's on the negative x-axis. And we'll have that, looks like our slope then is just going to be 1, so it must be at a 45-degree angle. So our normal vector should point probably either at another 45-degree angle. So either one of the two options where our slope is -1, if the slope of this thing is 1. But again, I've already taken the liberty of finding our parameterization. So those things can move between 0 and 1, 7 - 7t, 0 - 7t. I also found f of r of t and simplified it a bit. If you'd like to check that, just plug in those two options for x and y, and you should hopefully get the same answer I did. But I want to focus mostly on this new stuff because there's quite a lot going on. So let's dive right into that. So I'm after the normal vector, which the normal vector should be plus or minus. I want the y derivative of r in the x position, and I want the negative x derivative of r in the y position. I could have also put the negative on the y instead of on the x. It doesn't actually matter. As long as I put a negative on only one component, I will get a normal vector. It'll just change which orientation I have. And since we're going to be deciding on our orientation after we find one of the normal vectors, it's fine to put it on either spot. But I should plug some stuff in here. The y partial is -7. And then I want the negative of the x partial, which is also -7. So I get the vector, if I simplify that out, try one more time, I get the vector -7, 7. And it looks like I got so excited about finding a normal vector, I forgot to include my plus or minuses. So let's go back through and add those in. Which is fine because I usually think about the plus or minus part only after I actually have a normal vector. And then decide on the orientation that I need once I'm done. So I've got a vector right now. It points in the negative x direction and the positive y direction. So if I'm going to come and figure out the actual normal vector that I want to use, I'll remember I said that we wanted the downward flux here. So I'm going to take the negative option out of the plus or minus. So I want the negative of -7, 7. Because at the moment, my y component, or from the beginning, when I just found my normal vector, I had a positive value for the y component. which means that that's an upward oriented normal vector. And I wanted the downward oriented normal vector. So I want to have a negative value in that y position. I also need the magnitude of that vector in the denominator, which will be the square root of 7 squared plus 7 squared. Simplify that whole mess out. I'm going to get 1 over the square root of 2 times the vector 1, -1. Or again, important that the y component of that normal vector be negative so that we have a downward oriented normal vector. So 1 over root 2 times the vector 1, -1. If we had instead wanted the upward flux instead of the downward flux, I would have just used -1, 1 over the square root of 2 to be my new unit normal vector. And everything else in the problem will work out the same. I still need to get the magnitude of r prime of t, which is the square root of, looks like -7 squared plus -7 squared. Maybe keep my hat going because it was a little bit too short, which results in 7 square root of 2. So that's the value I'm going to plug in for the coefficient on ds. All right, and finally, I'm after the evaluation of that Flux integral, which if I plug everything in, I should get the integral we see down here. Since I've already done a few of the steps already, I'll go ahead and scroll down as I talk about it. I'm after f.dr, or f of dr, wait, I think I'm saying that wrong several times. F of r is the first part that I want in, because I'm then going to take the dot product of that with the unit normal vector. And then I'm going to multiply that whole thing by ds, which in our case, ds is 7 square root 2 times det. And from here, it just becomes a standard integral. I have a dot product of 2 vectors, which ends up being a scalar. I had multiples of 7 all over the place, so I factored out 2 of them. So factored out of 49. The rest of everything here is just a polynomial. Also notice I had a square root of 2 in the denominator times a square root of 2 in the numerator from ds. So the square root of 2 canceled out, which is important in a moment. The next thing we're going to look at is why that comes together. But then we just integrate that polynomial, evaluate from 0 to 1. I got 686 over 3, negative 686 over 3. If you had instead used the positive oriented vector instead of the negative orient or the downward oriented normal vector, you would have gotten a result of positive 683 instead of negative 683. So if you're doing a web work problem and you are pretty sure that you've done all the math right, try just multiplying your whole answer by -1 and seeing if it works out. Oftentimes that trick will work. So let's talk about a couple of things that are true in general. So if my parameterization R is just x of t comma y of t, which is how we define most parameterizations, right? There's an x component and a y component. Then the magnitude of r prime is just the x derivative squared plus the y derivative squared. Again, that's just based on how we do standard parameterizations. If we also look at the magnitude of the normal vector that we've been calculating. Remember that all that happens here is that the x and y partial derivatives switch places, and also one of them gets a negative. But if I'm looking at a magnitude, I end up taking an absolute value. So that's just the y derivative squared plus the x derivative squared, which ends up being exactly equal to the magnitude of r prime. So the derivative of our parameterization, or the magnitude of the derivative of our parameterization, is equal to the magnitude of the normal vector that we get from that parameterization. Meaning that we can simplify this Flux formula that we've been using to a point that we can actually calculate a Flux integral without needing to find a unit normal vector, which I think is a relatively interesting result of the way that this all comes together. So because our parameterization is sort of baked into our problem all the way through, we don't need to worry about getting a normal vector because the Flux integral takes care of that by itself. All we need is just the normal vector that's associated with whichever parameterization we're using. So in the end, we get this nice looking result out here that our Flux integral can be calculated by just finding f dot n, where n is our normal vector, not necessarily our unit normal vector, which can be quite nice. And again, I think that's a fairly interesting result that comes out of this Flux formula. All right, one other thing we should say about Flux is that Flux is additive, which means if I define some closed region, so I've got some closed loop C, which, by the way, when we've got the circle that's in the middle of that integral symbol for Flux, that circle is it's a thing that physicists and engineers care about usually more than mathematicians. But anytime the circle's there, it means we're still doing an integral. It's just that whatever loop or whatever curve we've decided to integrate along is a closed loop. So when we do a line integral with a circle in the middle, just means that our curve is closed. And later on, when we look at surface integrals that will also sometimes get a little circle in them, it just means that whatever surface we're looking at is a closed surface. But I digress. So when I say that Flux is additive, I mean that if we want to define our curve as the union of two separate curves, I'm giving the hemisphere over here as an example. I have C1 is the upper curved part of the hemisphere. C2 is the horizontal line that connects the two ends of the hemisphere together. If I wanted to look at the flux across C being the whole hemisphere, so I might be looking at the flux out of the region defined in that hemisphere, I can break apart that flux along the closed loop C into the sum of the two fluxes that go out of C1 and out of C2 and just add them together. Meaning I can just break apart my closed loop into a sum of integrals that are just over standard curves that may or may not be closed. So again, the flux through C is equal to the flux through C1 plus the flux through C2. We'll just have to make sure that we use the same orientation for both C1 and C2, which would mean probably in this case, we might use outward oriented normal vectors. So we just want to keep our orientation the same on both C1 and C2 in order to add up to the correct flux. So if we look at that idea in practice, let's come over here and look at the outward flux of the field given. It's xy plus y, xy comma y squared. It's going to go across the region defined by y equals x squared and y equals x for x between 0 and 1. And I've got a figure drawn over here to the right. So because we're looking at small values of x, small being less than 1, We have that linear equation, y equals x, is the upper equation, and y equals x squared is the lower equation, because x squared will just be below x if I have small x values. And we are interested in finding the outward flux from this region. So I'm going to split it up into the outward flux across each of the two sides. So I've got these green normal vectors for the outward flux from the line y equals x, and the blue normal vectors representing the outward flux along the line y equals x squared. So I'm going to need to parameterize both of those curves. If I'll start with y equals x squared, let x be t. That means that y, which is x squared, is going to be equal to t squared. So I get the parameterization t comma t squared. When I parameterize y equals x, I just get I get the parameterization t comma t. But now let's just focus on part A first. Looking at the outward flux across, specifically just that y equals x squared curve. So once I get my parameterization, t comma t squared, I'll need r prime, which is 1 comma 2t. Just take each of those derivatives. To get the normal vector, I just swap their positions and assign a negative to one of the pieces. But keep in mind that for that blue region, so coming out of y equals x squared, all of those normal vectors that are oriented out of that region are pointing down. So for the blue set of normal vectors, down is the correct orientation. Down and out are going to be the same orientation. So I want my y value to be negative. So I put the negative on the y component. So my normal vector is 2t comma negative 1. From there, I'm ready to actually take the integral, and that's just evaluation. So let's keep looking at the more interesting stuff for a moment, so we can still compare and contrast these ideas. So if I look at my other parameterization, which is tt, I get a derivative of that parameterization, which would be 1, 1. To get the normal vector, I simply swap the x and y derivative terms, which is still 1, 1, but I have to assign a negative to one of the two sides. But for the green normal vectors, again, we still want to be getting the outward flux. For those green vectors, the outward orientation is up. Again, up and down means that we're only really looking at the y component of these normal vectors. So I want a positive y value in the normal vector. So I'm going to assign the negative to the x value instead of the y value. So my normal vectors for n, that green n, will be negative 1 comma 1. All right, and then it's just simply a matter of evaluating this stuff. If we use that new simplified formula, all we need is f dot r dt for our integrand. So integrate f dot n, I said r. We only need f dot n dt, where n is the normal vector that we get directly from our parameterization. So plug in each of those pieces, and then these integrals don't end up being too bad. Just take their dot products, I get some scalar functions, integrate and evaluate from 0 to 1. Along x squared, I get a value of 1/5, and across y equals x, I get a value of 0. And so then for the final part, which is asking for the total flux, I simply need to add parts A and B together. So 1/5 plus 0 still comes out to 1/5.